In question 2 we have three sources of radiation, your alpha, beta and gamma, and they're emitted into magnetic field directed into the page. That's what the X's indicate. It's like the tail of a arrow or a rocket with fins heading into the page, and that's what you see. It would be a dot if it was coming out of the page, because that's the point of the arrow or the tip of the rocket. Anyway, on the diagrams, draw arrows to show the path of each type of radiation as it passes through the magnetic field. So this is a right-hand slap rule that you are applying. Although in reality alpha and beta radiation have different speeds, for the purposes of this question, assume they have approximately the same speed. Okay, so that adds a little bit of layer of complexity, that assuming that they have the same speed. So let's just get the general direction first. So alpha being positive means that the direction of a conventional current is to the right. That means your thumb goes in that direction, because I won't explain the principles, we're just doing the questions at this point. So conventional current to the right, fingers into the field, into the screen to show the direction of the ball. That means there's a slap upwards, so the force upwards. So it'll curve upwards. I'm just not drawing them on the diagram just yet, because we have to confirm something else. That means beta will go downwards. That's a quick way to look at it. But remember how we get that. That's a negative charge going to the right, which means it would be equivalent to a positive charge going to the left. So that means fingers going into the board with thumb going in the direction of the positive flow, even though it's negative in the other direction, but you know, old conventional current electron flow thing. That means it slaps downwards with your palm of your right hand. Gamma's easy. We're just going to draw it straight on, straight through. There is no deflection because there is no charge. Okay, now, so that's the first part. That gives the direction. But we've got alpha and gamma sorted. But we've got this extra layer of complexity, that alpha is a heavier particle and beta is much lighter. In fact, beta particle is so much lighter that it would take much less force to deflect it. Another way of putting that is the alpha being so much heavier, although here's the trick. The alpha has got a 2+ charge, so that means it should have twice the force, but a beta particle has got around about 1/2000, I think it's 1730 or something, times the mass of a subatomic particle, whereas an alpha particle has 4 because it's got 2 protons and 2 neutrons. So combined with a much higher mass and twice the charge, the double the charge means it'll interact twice as much with the field, but 4 times the mass means it's less likely to, it takes more force applied to change the momentum of that. With a beta particle being only -1 or -1 charge, it'll interact with the field half as much, but because that mass is so much tinier, it should take less force, much less force to deflect it. So we should expect a greater curve with the beta particle than the alpha particle, which should just get a gentle curve compared to beta. Okay. So moving down to B. Okay, give detailed reasons for each of the shapes that you have drawn in the above diagram. Well, we've kind of already reasoned it out, but we'll just recap because it's useful. We'll start with gamma because that's the easy one. There is no charge, so no interaction with the field. Really roughly, no interaction, therefore it passes straight through. Okay, alpha radiation has a 2+ charge, which means from the right hand slap rule. There are different other rules you can use as well, but I'd like to stick with the right hand slap rule because it's pretty easy to use, I think, in this case. Right hand slap rule, so that indicates it'll move and experience a force in the upward direction, and the large mass indicates that it will bend not so much. Okay, the beta radiation has one minus, and with the right hand slap rule, if you apply it for conventional current, or you could use some people use a left hand slap rule for negative charges, and as long as you know what you're doing and you're consistent with it, but that gives the direction of downwards. And the very low mass gives a larger bending. Now, one way you could look at this, because it's actually a factor of two things how the mass, how the bending occurs. You could look at the charge and the mass, and put them together as a sort of a ratio. Because if you were to look at it in one way, the amount it bends is proportional to the charge, and it's inversely proportional to the mass. So the larger the mass, the less it could be mass squared. But it's a relationship along those lines. So you could look at that charge to mass ratio and describe it in terms of that as well. Okay, moving on. C. Describe what each of the alpha, beta and gamma radiation is, and discuss what happens inside a nucleus when it produces each of the three types of radiation. In your answer you need to state what happens to the atomic number and the mass number. Okay, so there's two things we have to do here. What each is, so we're going to describe the is, write that on each of them before I forget, and discuss what happens inside a nucleus when it produces. So we've got to look at the production of each. So it's produced, and it's produced. So that's going to prompt me. I've read the question and I'm not going to forget what I'm supposed to answer. And when I'm talking about the production, I also need to state what happens to the atomic number and mass number. So production, we've got atomic and mass. And we've got atomic again and mass. And atomic and mass. Okay, so let's launch into it. We've got alpha radiation is a helium nucleus. It's a nucleus because it doesn't have the electrons, and when it's produced, during radioactive decay, the nucleus that emits it gives off this helium nucleus. So the atomic number of that is 2 and the mass number is 4 because it has 2 neutrons. So 2 neutrons plus 2 protons adds to the 4. Yeah, that keeps it really simple, I think. Beta radiation is a high-speed electron. High-speed electron that's been emitted has atomic number. Now this is a tricky one because it's just an electron. It doesn't really have an atomic number, but we sometimes write -1 to show that in an equation that a beta particle has increased the number of neutrons while decreasing. Hang on, I got that around the wrong way. Increase the number of protons while decreasing the number of neutrons. So overall there's a 0 change in the mass of the nucleus, but the charge increases by 1 because the beta particle is an electron coming off out of the nucleus. And yeah, anyway, so what happens, basically a single neutron in the nucleus becomes a proton, positively charged, plus that beta particle which has got a single negative charge, and it has that atomic number of 1, so they sometimes write -1 up the top just to show what's going on here. Anyway, gamma radiation is it's just EM radiation, high frequency. So high frequency, and the atomic number doesn't change, mass number doesn't change. but what usually happens is there's excess energy in that atom, and that energy is just given off as radiation. So that's how gamma radiation forms. It's pretty exciting, really. I think that's the rest of the question. That is. There we go.